Welcome everyone to round two, part two of the technical introduction to blockchain with Laurence Kirk of Extropy.io. For those of you newcomers, if you're wondering about the first event, there are the slides on our Medium, and there's also a YouTube recording of Lawrence's talk from last night. So just find that on our YouTube channel or our website. Oh, welcome, Vivian. Welcome, welcome. Please ask questions in the chat. Keep the chat going as well. So like post something cool about yourself, what you're up to, what degree you do, where you're from. Last night we had someone all the way from Brazil. So, you know, just to show that this isn't just, you know, within the square mile of Oxford and everyone's obeying their residency requirements to meet their degree. Before I hand over to Laurence though, Anthony from Encode Club would like to pass on some information about some exciting events they've got coming up with us. So over to you, Anthony.
Thank you very much, Brandon. Let me share my screen. Hi, everyone. I'm Anthony. I graduated from Oxford a few years ago and help out with some of the stuff with the Blockchain Society. Very quick thing, so you can get on to Lawrence's fantastic part two. We run a blockchain hackathon that lasts 10 weeks or so that we run with pretty much around the world now. It originally was just 6 UK universities, one of which was Oxford. Now it runs at about 50 different universities, or it's open to 50 different universities and students. It's a blockchain hackathon. We teach you about blockchain. We educate you about all the different projects and companies in blockchain, and we set some fantastic challenges for you to do, and we give out a shit ton, if I may, pardon my French, of cash prizes. We give out anywhere between 50 and 100k per hackathon to smart people. And the coolest thing is that in our last hackathon that finished in August, the winner was from Oxford, a postdoc in evolutionary biology, and raised 800k investment pretty soon after that. So not only did he or they win the hackathon, get about £5,000 worth of cash prizes, they also raised investment. You're allowed to answer one of the technical challenge to do with blockchain, or build your own idea. If you've ever thought about you want to build your own blockchain or your own blockchain application, we will help you do that. You will be supported by weekly workshops, much like Laurence's brilliant one tonight, some technical support and one-on-one support from our team. And we have some nice, juicy overall prizes on top of the prizes that are available per challenges. It's open to everyone. So if you're not necessarily a student or researcher, you still can take part. We allow everyone into the hackathon. And if these names mean anything to you, they are quite big, particularly Avalanche and Polkadot are two of the biggest competitors to Ethereum out there at the moment. So we encourage you to register by the 9th of November. We keep registrations open until mid-December, so you've still got a few weeks to decide if you want to, but you will have roughly 10 weeks from the 9th of November to build something and submit something in mid-January or by mid-January. We are a community of university students, researchers, hackers. We've been doing this for a while. My background is investing in work for an investment fund, investing in projects. So we use this as ways to find cool stuff to invest in. We also help people get jobs and in general, learn about blockchain and support fantastic societies like Oxford Blockchain. So guys, if you're interested, go to the website. It's hack. I'll put it in the chat, but it's hack.encode.club. You can register here, and it should, if all is working fairly well, take you nicely to a simple registration form to register. You may register as teams, you can register as individuals. We'll help you find teams if you don't have, or you can take part as an individual. So we've had a lot of entrants from Oxford in the past, a lot of people doing well, and I expect that to remain nice and strong moving forward. So yeah, I'll answer any questions that are in chat, but otherwise I'll hand back to Brandon to introduce Laurence.
Thank you, Anthony. Yeah, so last night, Laurence introduced everyone to key concepts such as consensus, building trust, open systems, and programmable blockchains. He's going to delve a bit deeper into those tonight. And I think we'll be able to get our feet wet with a bit of code in the next event. So get ready for that. No need to worry about compilers or downloading development environments, it can all be run from the browser, and we'll sort you out with that next week. But over to Laurence from Extra.io, CEO and senior blockchain developer there. So once again, Laurence, thank you, and over to you.
Pleasure. Thanks, Brandon. Thanks, Anthony, and thank you all for coming this evening, coming back. We have plenty of time today, I think, so we don't need to rush. So there's plenty of time for questions. So please do ask them as we're going along. If I don't see them in chat, because it's sometimes difficult for me to see the chat, please shout them out to me. I'm very happy to answer questions as we're going on. Okay, so let me just share my screen. Oops. No, it's not letting me do what I want. Okay, let me try something else. Slides. There we go. Okay.
Yeah. Awesome, Laurence. You are live.
Great. Okay. So, yeah, I've told you about myself yesterday, but there's some details if you want to contact me. If you have further questions, yeah, please email me. I'll have a look at our website. We also have our website all about education, which I'll give you the link to at the end as well. What I'd like to talk about this evening, it's all about smart contracts, programmable blockchains. So we'll have a little recap of what I said yesterday about smart contracts. We'll look at some of the languages involved that you can use, and then we'll concentrate on one language in particular called Solidity, and I'll go through an example smart contract. We can write that together, and I can explain all the parts of the Solidity language and what makes up a smart contract, and then I'll put in some do's and don'ts for programming smart contracts as well, what you need to be aware of. Perhaps we should start with if there are any questions from the first session. I did answer some, but if you have any others, I'm happy to do a quick review now. Okay. No, okay, so we'll go on, look at smart contracts. So yesterday I spoke about the development of blockchains and said we had Bitcoin in 2008, 2009, and then the area was didn't really make much progress. We had lots of altcoins and people trying to move what Bitcoin did forward, but the next really big step came in 2014 with Ethereum. Some people call the world computer, and I have, as I was explaining yesterday, you should think of this not as distributing computation to be done amongst different people who are all doing different things, but really a particular computational task that is done by everybody at the same time. And we do this because we want the essence of the features of the blockchain, things like transparency and verifiability. So all of the nodes on the Ethereum blockchain run virtual machines, and they're able to run small applications called smart contracts. And whereas with Bitcoin, we're thinking about the movement of value between different people, and we're tracking that. That is the state of the Bitcoin blockchain. With Ethereum, we're tracking the state of these applications, in particular, the state of these smart contracts. As I said yesterday, just to recap, smart contract, an Ethereum smart contract is a piece of code running in the Ethereum virtual machine. The environment they run in is highly restricted for various reasons. The contract itself has three main parts. It has the code, the actual code, the functions that we're going to call. It has some state, so these are variables in the contract, in your application. And it can also have a balance of ether, which is the the cryptocurrency that belongs to the Ethereum blockchain. They're called contracts, but they don't necessarily represent a contract between parties. And as you'll see, we write them in higher level languages, such as Solidity, and they're compiled into bytecode. And that bytecode is what is kept on the blockchain. And the process that we go through to create and run smart contracts is that, for example, Alice decides she wants to write a contract, so she creates it in whatever language she likes and compiles it into bytecode and then submits that as a transaction into the blockchain. And that, thanks to the peer-to-peer network and the gossip protocol, that contract is gossiped around the network. Of course, it's slightly more complex than that. Initially, it goes out as a transaction. That transaction becomes part of a block, and it is the block itself that is passed around the network. But at the end of that process, every node on the network will have a copy of Alice's contract. And then if Bob wants to call a function in that contract, he will send a transaction to call a function. That transaction will get passed around the network. Again, it will then get put into a block. The blocks will get passed around the network. And then within that block, the transactions will be processed in order by the virtual machine. So every virtual machine on the network will take the transactions in the block and go through them one by one, running those transactions, running the functions that those transactions are calling, then passing in the parameters that Bob chose to pass into the functions, and going through those until they reach the end of the block. And that's the running of those transactions will then update the state of the contract. But because we have determinism, everybody everybody on the network, all those smart contracts will end up in the same state. And it is very important that they all end in the same state after the transaction is applied. Okay, one thing that is worth noting, an important distinction, is that between types of functions. And we'll see this when we write our contract. But if you take the example where Bob wants just to read data from the blockchain, then he doesn't need to send in a transaction to update the blockchain. His local node that he's using, we can assume it is synchronized and will have the data that he wants to read from the contract. And so he can just connect to a node on the blockchain, read the data from that node. So effectively he's calling a function which will send back data for him. But because he doesn't want to change the state of the blockchain, we do not need to create a transaction that is passed around the blockchain. We can just read it from our local node. We don't need to come to any kind of consensus because we're not making any alterations to the state of the contract. So this is an important distinction that you need to bear in mind when you're writing your contracts, and we'll see how Solidity has a special keyword to show this. Okay, now I mentioned there were restrictions on when we're writing our contract, and when you're coming to something like Solidity from a traditional programming background, you'll find that it is much more restricted. You'll find that it is much harder to do things in Solidity and in smart contracts than it would be if you're writing, say, a JavaScript program or a C++ program. The first restriction we have is something called gas, and this relates to the amount of computation that your smart contract will do. Now, the reason for this is to prevent denial of service attacks against the network. If you imagine without this restriction, someone could upload a malicious contract which had an infinite loop in one of the functions, and then call that function, and then all of the nodes on the network all of the virtual machines would then have to do the same thing. They would all be running this function, which would just carry on forever. And so you would effectively stop the network running. And so we introduced this idea of gas. What this is that when you run a function in Ethereum, each computational step that you take within that function has a gas cost associated with it. When you send in a transaction to call a function, you have to pay up front for the gas that the function is going to use. So you're paying up front for the amount of computation that your function is going to use. And you pay for that in Ether, so the cryptocurrency for Ethereum. And because you can, this is tradable on exchanges, this has a real world value. And so every time you make a transaction on the Ethereum network, every time you try to use a smart contract, there is a real world cost to this. This is effectively the transaction costs that you see in Bitcoin, for example. And this fee that you pay up front goes to the miners of the blocks, but it is really there to not only reward the miners, but also to prevent denial of service. Now, if when you're running your function, if you haven't provided enough gas, the virtual machine will keep track of the amount of gas you have left as you step through your function, as you do your computation. If that amount that you have left reaches 0, then the virtual machine will stop the function at that point. It will revert all of the changes that you have made. So it will be as if your function never happened. The only thing is that the gas that you provided will be lost. So that gas will go to the miner. So you will still pay for that. So you should always make sure that when you're starting a transaction to call a function, that you have sufficient gas for that. Then the amount, the fee, the cost of that can vary. And this defines the cost of a transaction on Ethereum. And this varies quite considerably over time. And particularly over the summer, when we had a lot of people using decentralized finance applications, the gas cost rose considerably, and to the point where it could be you could be paying $20 for a transaction or even more. So you can find out, there are websites that allow you to track the gas cost, and it is something when you're developing your smart contracts that you need to bear in mind, because your end user will be paying to use your product, and so you want to make sure that they're not being disincentivized from using your application by the high cost of transactions. Okay, so that's gas. The second restriction we have is determinism. And this, as I said, is because we want the state of our contracts to be the same throughout our network. So every virtual machine, after processing a transaction, has to come to the same state. And what this means is that we cannot do anything on our virtual machine that may be done differently on different virtual machines on different hardware. So, for example, you cannot look at the local file system because that will be different on different machines. You cannot go to the internet to get data because some machines may be behind a firewall or may not have the ability to get to various internet sites. You cannot even do floating point arithmetic at the present in Solidity, because this can be done implemented differently on different hardware, and so there's a possibility that your calculations would end up different. So this does restrict very much the amount how we do write our applications. We do a lot of integer arithmetic in Solidity. Also, random numbers. We can't do random numbers because obviously they will be different on each virtual machine. This is a big drawback to if you're writing a gambling application. There are ways around this, but it does present a problem. It may be that you will use an oracle to get a random number from an external source, or there is, a contract called RANDAO, which you can use for random numbers. Excuse me. Okay, so as I said, oracles are third parties, trusted third-party applications that we use to fetch data for us from external sources. So they will go to an external data source, perhaps something giving you exchange rates, and they will then put those into your smart contract. But they do this as a transaction, and this ensures that every virtual machine on the network will get the same data. And to incentivize them, you're going to have to pay them for their services. There are a number of different ones around. Oracleize was one of the first ones, but now there is, you also have Chainlink, who offer oracles and oracle services, and Tola. There are a number of different ones now. Okay, so the environments in which our smart contracts lives is the Ethereum virtual machine. It's the specifications for that are given in the Ethereum yellow paper. It is a simple architecture, I guess. Its architecture is perhaps not the best designed. It was written in a way that perhaps was done very simply, but certainly doesn't make use of some of the more recent improvements in virtual machine design. But it is what it is. There are some, the architecture of it does give some restrictions or features to your contract. For example, everything is based on 256 bit words effectively, so everything is done on 256-bit arithmetic. Generally, we don't have to think about that when you're writing in Solidity. If you do a lower level language, you're using assembler, then that becomes more pertinent. Yeah, you don't need to know much more about that for what we'll do today. There's a diagram here of it that someone kindly supplied. This really just shows some different areas. On the very left, you have what is stored on the blockchain. So this is really the state of accounts, the state of our contracts, really, and obviously the blocks. In the middle there, we have what is happening in the Ethereum virtual machine itself, and the process we go through. As we're going through a function, we're calling opcodes and running computations. And then we have the caller of the contract as well. So they will send in, there will be some information about the caller and the transactions. There are some available variables that are available to you in your contracts that you can use, such as the address of the person that called your contract, the block number, the block timestamp, things like that. Thinking of languages themselves, yeah, this is an incomplete list. So on Ethereum, the main ones are Solidity and Viper. Solidity looks, I guess, like JavaScript. Viper is more like Python, but we'll be just looking at Solidity today. If you look at other blockchains, they sometimes use traditional languages. So Solidity was invented just for Ethereum, but other blockchains such as Hyperledger and EOS, they use traditional languages. Before you write your smart contract, it is worth thinking about the design of the application, and this can be quite a tricky thing to get your head around. So if you're used to writing applications, for a centralized application, adapting that to a decentralized system can be quite tricky. And to show you an example of that, we can think of the game rock, paper, scissors. Now, to write this as a centralized application is quite simple. I just answered one of the questions. Yeah, Rust. Rust is a good. It is a safe programming language. They have great memory safety. It's perhaps quite difficult. It has quite a steep learning curve to use it. I don't know a blockchain that uses it for a smart contract language. The Parity client for Ethereum was written in Rust. But yeah, I don't know of any ones that are being used as smart contract languages. Yeah, so to go to rock, paper, scissors, if you imagine trying to write this as a game on the Ethereum blockchain and write a smart contract to do this, if you did it in a very naive way, perhaps you would have the following approach. So you'd have a smart contract that is keeping track of the game and the track of people's moves, and maybe paying out a reward to the winner of each round. And you can imagine Alice would, if she goes first, she would play her move. So, for example, she would send in a transaction with the move rock. So that transaction would go into the smart contract. But the obvious drawback to this kind of naive approach is that transactions and their parameters are transparent. Everybody on the blockchain can see all of the transactions and the parameters involved. So if Alice plays this move, then Bob would be able to see the move that she has played. He would be able to see that her transaction was the move rock. And so it's trivial for him then to find a winning move against that. So he would, in his transaction, he would submit a paper to the smart contract, and therefore he would win. And it's a guaranteed win, and the smart contract would pay him his prize. But it's a guaranteed win for him. Whoever goes first is really guaranteed to lose in this situation. So we'd have to do something to fix this. One way we can do this is to use something called the commit and reveal process. And this partially solves our problems in that what we can do is we can use hashing functions. So we spoke about hash functions yesterday. And the smart contract could, instead of taking a plain text input, it would take the hash of the move that Alice would want to play. So Alice would play rock, but she would send in the hash of that to the smart contract. And if she did this, Bob may see that what Alice has done, but it's not in plain text, so maybe he doesn't know what she has played. So he then makes his move. So he commits, he plays scissors, so he sends a hash of scissors. And this stage is called the commit stage because we're saying what our moves are in advance to the contract by sending a hash of that move. And then in the reveal stage, we have to repeat the process, but then we send our move in plain text into the contract. And the contract can take these plain text moves that we've made and check those, take the hash of those and check those against the hashes we made in our commit stage, check that they are correct, so check that we haven't cheated and sent in a different move. And if those match up, it can then decide on the winner. So it can verify that Alice made a correct move. She made the correct reveal for the commit that she sent in. The smart contract can verify that and then decide that she is the winner and send out her prize. Oops, that's right. So that is a partial solution to the problem, but it's not a complete solution. Bob could still cheat because he could, knowing that there's only 3 possible moves in this game, he could take the hash of those 3 alternatives and work out in advance what Alice is going to play, or potentially what Alice's transactions could be. And when Alice does make a commit and does send this hash, he could work out what her move was going to be. So it's not a complete solution for this. So these are the kind of questions when you're writing something, when you're writing a smart contract. These are the kind of ideas that you have to think about. You have to really assume a very adversarial environment, and that people will try to cheat and try to break your contracts. So you have to make sure that you write your contract in a way that it cannot be broken, that people cannot cheat it or game it in any way. In addition to being able to win the game by working out the moves that they're making, there's also the possibility of stopping the game. So if your smart contract is written in such a way that it is waiting for a move, then you could have a situation where Bob could start off the game, but then go away and not play the next part, not play his move, and therefore stop the whole game, either maliciously or perhaps accidentally. Maybe he would lose his connection to the internet. So again, these kind of questions are ones that you have to think about and solve for your smart contract. Okay, so let's have a look at a contract. So I'm going to now share my screen, and we can go through looking at the Remix environment. Stop that. Stop that. And instead I'll share.
Lawrence, I think we have a question from Akanksha. Is it easier if I unmute you, Akanksha, just to ask the question? Hold on.
Hi, can I ask a question?
Sure.
Great. So I really understood the concept. The pictorial representation was great. I just wanted to ask, we just had a lecture on this today, and we understood that in blockchain technologies, your identity remains anonymous.
Mm-hmm.
So Bob would never know it is Alice technically, unless, like, if it's a multiplayer game, he would never know who he is playing against. Is that the case? Like, that was a contradicting fact that was going on in my head when you mentioned the whole example. So
okay, yeah, thank you. That's that's a good point. So generally, identities on the blockchain are perhaps not what people think they are. So people tend to think they're, for example, on Bitcoin and Ethereum, people tend to think they as real people are anonymous. It's not quite true. There's a pseudo anonymity. So your identity, certainly on the Ethereum blockchain, is given by your Ethereum address, which is derived from your public key. So you create a private public key pair, and that public key is then used to derive your address. And this is used as the simplest form of your identity on the Ethereum blockchain. Now, people think that they are anonymous, and particularly with things like Bitcoin, they think they're making anonymous transactions. That's not necessarily true, and there are companies that work to track things like money laundering on the blockchain, and do forensics on the Bitcoin blockchain, for example. And they do have some success using very statistical techniques in tracking who people are in the real world, or often identifying where addresses, how addresses interact with each other, and maybe which addresses are in fact the same person, and then using that kind of information to track down people. So in the case of our game, yes, Alice and Bob would be represented perhaps by just an Ethereum address, so just a large number. But also maybe in your smart contract, you would give the opportunity for people to associate a name with that address. And so to that extent, they could have some kind of identity. And then also there are companies who are addressing this to help people put their real world identity onto blockchains and to, to allow you to have a real world identity on the blockchain, and to associate your real world documentation, perhaps your passport, your driving license, use this to prove some identity on the blockchain that represents you. So I hope that answers your question.
Yes, definitely, that definitely answers my question, because now it makes more sense how your identity could be revealed. And eventually, in some applications, you would need anonymity. For example, if you're building the future of a voting application where you need to remain anonymous, but still need to formally verify, that's a complicated process. I mean, maybe if you go in that direction, this would really help. But yeah, if you've seen the latest online banking accounts, they just require some ID and then you are done. So definitely, that makes complete sense. Thank you so much for answering.
Pleasure. Yeah. So yeah, that's quite right. The onboarding process is still one that puts people off from using blockchain to some extent. It can be quite onerous. But I think there's going to be developments in these areas, so it's going to be an interesting time. Okay, so I'll just share my browser. So hopefully you can see that. Let me find my chat again. Okay. Okay, so the environments that we're going to use to develop our smart contract, the tool we're going to use is called Remix. And to use it, you just have to open a browser and go to the address remix.ethereum.org. I'll type that into the chat. It's capitalized it, but I won't. Yeah, so if you want to code along as I'm doing this, please feel free. This is a great tool to start with because you don't have to download any software for this. You don't have to install anything. There are other tools, and next week we'll see some of those. But this is a very good place to start. It gives you good feedback as well, and when you're learning Solidity, I think it's a great tool. You can do everything with this if you want to. You can write a smart contract and deploy it to the main Ethereum network if you want to. So, but generally, I think it's useful when you're initially developing a contract. I'll just check. I've got some notes. I want to make sure I'm covering everything. Yeah. So the another useful thing, which what's this? Another useful tool that you may want to use. We're not going to use it this evening, but it is useful. Is the Metamask plugin for your browser? So this is a wallet that you can use. It's a plugin. Looks like this. I'm not sure if you'll be able to see that. I'm not sure if plugins will appear when I share my screen. But it is a browser plugin. It acts as a wallet, and you can use it to sign transactions. So if you're interacting with the main Ethereum network or some of the test networks, then you can use the MetaMask plugin as a means of doing that. But this evening, we won't be doing that. We'll be using just an in-memory and in-browser blockchain that doesn't connect to anything outside the browser. Okay, so we'll start off with a quick tour of Remix. So on the very left-hand side, we have an area where you can add plugins to the environment, and there are two that you will definitely need if you're going to write a smart contract. So there's the two I have here. To add those and to add other ones, you click the plug, and that brings up a list here of all the possible plugins. So I've just installed or activated two. So the top one here, that's the Solidity compiler. So you definitely need that. The second one is the kind of the environment that allows you to run and deploy your contracts. So you'll need those two definitely. But there are plenty of other ones, some very interesting ones, some involved around security, static analysis, that kind of thing. But we will just look at those two this evening. Okay. And then this part here, if you click the little files, this is your file explorer. So when you want to write a contract, a new contract, you can click this little plus sign here, and this will bring you up a new file. You can give it a name, and that will bring up an area in the large area here on the right, where you can write the source code for your contract. And then you can go through, these are all stored in the browser effectively, but you can store them on your local file system as well. So this is just the source code we're talking about here. We're not interacting with the blockchain yet. This is just the source code. But you can write your contracts and have them here. So you can see I've got some other ones here. I'm going to look at this one this evening. So that's the file explorer. If you look at the Solidity compiler, you just click on the icon there and it brings it up here. It is trying to compile my contract because I opened a different contract, then moved back to this one. If I close all of those so it doesn't try to do too much. So this is what you'll see when it compiles. You'll get a green tick from that. And then the other part we have here is a section that you use to deploy and run the transactions. So when we have a compiled transaction, it will appear here where you see contract, and then we can deploy this to a particular environment. And I will show you how to do that when we have a compiled contract. Okay, so we'll go back here, get our Solidity compiler ready, and we'll start writing a contract. So I've already created a file for this and called it score.sol. The contract that I'm going to write is very simple. It's really trivial and perhaps in the real world not very much use, but it is just to introduce you to the Solidity language. Okay, so really this is the very simplest thing that we can have that is going to compile. So at the very top here, we have this line which defines the version of the compiler, the version of Solidity we're going to use. Excuse me. So what I'm saying here is that we're using Solidity from version 0.7 to 0.8. So I would just recommend just copying this. When you write your contract, just copy this. This will bring up the latest version of the compiler is 0.7.4. So this will pick up the latest version of the compiler, the latest version of Solidity, and that'll be fine. Second line down is really a comment. You don't have to include this, but it allows you to put in details about the license that your contract will have. So if you're thinking about this is open source, you can put in some metadata here about your contract in the license. If you don't include this, it will give you a warning. So I've just included one there so that you don't get any warnings. Generally speaking, I would say use the compiler and use the warnings. It really will help you. The compiler definitely is your friend. So it will tell you when you're doing things wrong, and it will make suggestions. They may not be the most helpful of suggestions, but you should definitely take note of them. If you've got errors, then obviously you won't be able to proceed. But even warnings, I would definitely look at them. So I wouldn't hide warnings if you get them. Definitely look at the warnings it is coming up with, because it may be a good indication that there is a better way to write what you want to do. Okay, so we write our contracts. The next line we have is what defines our contract. So we use the keyword contract, and then we give it a name. So this is my contract. I'm going to call the contract score, because I'm going to use it to keep track of a score. And then we use braces, curly brackets, to show the limits of our contract. So we're going to write the code within these braces. And because I've followed the syntax properly here, I'm not getting any errors showing. If I misspelled the keywords, I get more to compile. If it's not very responsive. Okay, there you go. If I misspell the keyword or make a syntax error, then the compiler will warn me. I should get a little indication on the line that is wrong, and I'll also get an error message on the bottom left here, giving me some more details. Okay, and it does also suggest, give you some suggestions as well when you're writing the contract of keywords and variables that it knows about. So they can also be used to autofill. Okay, so that's the most basic contract you can have. It's a completely empty contract, so it's not a great deal of use. Oops. I'm going to start adding to this. Now, I'm going to do this. I'm just going to copy and paste some pieces in rather than typing them. It's just a quicker way to do it. But what I'm going to do, first of all, is introduce a variable. So I'm going to introduce some state into our contract. And this state is preserved. Okay, yes, I can copy it into the chat as well. Perhaps what I'll do is give you the contract at the end, or perhaps partway through, rather than doing it line by line. Maybe Oh, no, effective like that. My God, here we go. So I'll copy that. There you go. So this is this is a variable in our contract, and this is some state in our contract, and this is preserved between function calls. So if you set this score to be a certain value, then that score will be preserved in the blockchain until it is changed by somebody calling a function to change it. Now, it's an important thing to note that Solidity is a typed language. So when you declare a variable, you have to declare the type of the variable as well. And this first word here is the type of our score variable. So to decode that, what it means is it's an unsigned integer, and it's size 256, which is the maximum size. So this is as large a number as we could want. We could certainly use a smaller number, but just for convenience, I'm going to use this type. If you miss out the 256 and just say uint, it will still work, but it will default to 256. But you can have different sizes. You can have uint 8, etc., anything up to 256. Okay. So that's a variable. So now our contract has some state. So we're adding to it, but it's still not very useful. We cannot easily read this. We cannot write to it at the moment, so it's not much use. So the next thing we probably want to do is to be able to read the state from the contract. So to do that, what I'm going to do is to add a function to read the value of the score. So let me just get that. So here's my function. So this is the function that somebody could call to find out the value of score in our contract. So we start off a function with the function's keyword. We then have the name of the function. That can be anything you like. We then have a space within the parentheses for any parameters. For this one, we don't have any parameters, so we don't have anything in there. We then have some keywords, which I'll explain in a moment. Then within the curly brackets, we have the actual code that we're going to run. So what this function is going to do is it's going to return the value that we have in our score variable. Now, as I mentioned earlier, it's an important distinction to make between functions that just read some value from the blockchain and functions that try to change the value on the blockchain. And so that is why we have this view keyword here. So what this keyword is doing is saying that this effectively is a read-only function. So if we took away the view keyword, that would mean that this function could be used to write a value to our contract. And you'll see when I take it out, the compiler has realized that even though we've said this is potentially a write function, that we're not actually doing any writing. So it's suggesting to us that we make it a view function. So that's what we'll do. Okay, and then the next keyword is one that you will need for every function. And this shows the visibility of the function. And if we remove this, we get an error. So we have to have that. It doesn't just give us a warning, it will give us an error. So every function we have will need a keyword to show the visibility. And the visibility for this one, whoops, I've said is public. The choices we have are public or private and internal and external. And of these, public is the most permissive. It really means that our function can be seen from anywhere. It can be seen from within the contract. It can be seen from outside of the contract. It can be seen from derived contracts, as we shall see. It really is the most permissive. This thing, anybody can potentially see this contract. We could, an alternative to this one, that the most common one I think you would use would be something like external. This means that this function can only be called from outside of our contract. So, for example, if you have a web page that is making a call into your smart contract to read this value, this external keyword would allow that. But it would mean that another function within the contract could not call this function because this is purely external. And it's very useful. It's a good design principle to be labeling your functions as internal and external as much as you can, just so that you then get a good idea of the interface that your contract presents to the world. So if you have your external functions together, you will have a good idea of what an outsider how an outsider can interact with your contract. But I'm going to put that back to public for the moment. And then the next keyword we have, this returns, shows us the return value from our function. So because we want to return our score, and that is of type uint256, then we need the keyword returns, and we need to say what the data type is for that return. Okay. It is possible also to put a variable name in here, so you could have something like this if you want, but it's not needed. You can just have the data type. Okay, and as someone said in chat, yes, you can, for comments, yeah, you can use slash like this to make comments as you're going along as well. Okay, so that's the very simplest function really that we can have, but this means that now our contract can actually read the score. We can read some state of the contract from it. So it is usable to some extent, even though we can't actually change the score. So if we deployed the contract, this score would get a default value of 0. So everybody that called the getScore function would end up getting back a value of 0. So it works, but it's not very useful. Okay, maybe a good point for us to take a break. I know that people asked to have a quick break in the middle of this talk this evening. So I think that's probably a good point to do that. If we take just over 5 minutes, so if we come back at 18:35, just to give people a chance to have a break, and then we'll look at other types of functions and other types of variables in Solidity. Or if you have any questions you want to ask in the time as well, please do. Yeah, the compiler, yes, so it picks up a compiler. So there are, as you can see at the top here, there are various compilers available that it can install. So if you wanted, you can go back to a very early compiler. But yeah, so you can choose the one you want. But it's all there within the browser. Yeah, it's not relying on any external compiler to be installed. Yeah. So to answer the Bashir's question, so you say we selected the 0.7 compiler, or can we select what we wish? Yes. So on the left here, you can select the compiler that you would like to use when you're compiling your contract. The statement at the top that I have saying 0.7 means use any compiler from 0.7 to 0.8. So it will, we'll be happy to use 0.7.4, but we could choose a different one. If we chose 0.6, for example, this is probably going to give us a problem. So it's not happy. Oh, no. Oh, it's gone back to 7.4. Okay. Yeah. So, yeah. Generally speaking, you just leave that to be the latest version. There are some language differences between the major versions. So if you had something very specific, then you might want to go back to an older version, but generally not. So the question, how long the session will be? So we have almost another hour to go. Yeah. So I'll finish at 7:30. Okay, so we'll continue now. One thing I should mention, the documentation for Solidity is quite comprehensive. It's quite well written. If you go to solidity.readthedocs.io, I'll just paste that in, then you get the documentation. It's well worth using that. So you'll probably want to use that when you're writing Solidity to find out the exact details of what you're doing. There was a question. Date. So how is the date coming to a variable? So dates are a little tricky because the concept of time on the blockchain is something that's rather nuanced. So if you want to get the time that your function is running, then you can get something called the block timestamp. So this gives you a time that when the block was produced. So when your function is running, and that was as part of the block. The only problem with that is that this time is input by the miner of the block and is not necessarily very accurate. I mean, it's accurate to some extent, to I guess a few seconds perhaps, but it may not be more. It does have a margin of error at which the block would be rejected, but it is done via the miner, so it's not something that you can necessarily rely on. So often people, rather than using the block timestamp, may use the block number if they are trying to show maybe the order of some event. And then dates, yes, you can use, there are some libraries available. So people have written other smart contracts that your contract can call, and some of those have functions for handling dates and doing date and time manipulation. But yeah, so bear in mind the caveat that the time might not be exact. Okay, so we have a question about the differences in designing centralized and decentralized apps from the point of view of a developer. So yes, that's a very good point, and there's quite a number of differences, I guess. So if you have a centralized application, then you are in control of that application. You can easily modify what that application is doing, and you can easily restrict the people who are accessing your application. So decentralized applications are in a much more hostile environment, and once you have written your smart contract and deployed it, it is out there and you cannot change it. The contract itself is immutable. You cannot change the code that you have written, so you have to be very careful that the code is doing exactly what you want it to do. The other things to bear in mind are that your code, the smart contract code, can be called by multiple unknown people. You won't necessarily know who they are, and I'll come on to that in a moment in how we write our contract. But by default, certainly, for example, the way I've written this function, anybody in the world could call this function, and you don't necessarily know anything about that person. So you have to be very careful about that when you're writing decentralized apps. There's also the case that the way the application runs is via transactions. The order of those transactions cannot be guaranteed. They are chosen by the miner, so you should not make any assumptions about that either. I think the best example is perhaps the one I gave with rock, paper, scissors, to show you how different it is to write a decentralized application. If you'd done that as a centralized application, it would have been much easier to write. You could have much more easily controlled the behavior of the participants in the application. Okay.
Thanks for your answer there, but I just wanted to ask one more thing. This assumes that the code is always correct, which it almost never is in real life because it always has bugs. For example, the case study we did today was the DAO's code base, which was hacked, and then about $50 million were taken away in Ethereum.
Yes.
Yeah, that's the whole situation. That's how it happened. So even though with a lot of people, a lot of community building up apps like this with so much security, it is possible that they can be hacked, right?
Well, so I think the example you're talking about is the DAO, the attack on the DAO. Yes, so certainly you can have bugs within your smart contract so that your contract may act differently to how you intended. But so there is that kind of attack that can be done. So someone can manipulate and call your contract in a way that is to their advantage and against the intention that you had when you wrote the contract. But the code itself cannot be altered. So to that extent, it can't be hacked. So traditional hacking may involve changing the code that somebody's calling so they're actually running a different piece of code to what they're expecting. So from that point of view, you can't do that. And that is one of the advantages of smart contracts. And because they're on a blockchain, you can always be sure what code it is that you're running. But in the hacks that have happened are all down to people having bugs within their code. So it's not an attack at the protocol level in any way. It's not that there's any problem with Ethereum. It is the fact that what they wrote had bugs and didn't behave as they expected and led to an undesirable result. Yeah. So for example, someone being able to withdraw a great deal of money from the contract, which is not what they wanted. But that was just because they didn't foresee how the contract would be used. I will talk a little bit more about security a little bit later on. But I'll continue now about the functions. So we've written a function to get the score from our contract, but that's not so useful. I mean, that's useful, but we need something also to change the score. So I'll add a function in here to change the score as well. Put that into okay. I've got an extra here. Error. Okay, that's one. I've got a little bit more in my function than I intended. Okay, so yeah, this is the basic one. So this function takes in is what we want to use to change the variable score. So this is a function that is going to be called as a transaction, and it's going to change the state of the blockchain. It's going to specifically change the our value score. And so it's quite straightforward in how it works. So we pass a parameter underscore score here, which is then set to be our value score. And I've declared it as a public function. We can return a value from this, although we don't have to. And I should point out that, and we'll perhaps see more of this on next week, that even though we return a value from our function, it is not easily seen it's certainly not seen within the contract, and it is more difficult to see what this function does. So from an external point of view, if we call this function to set the score, that calling application would not see the result of this function, because that calling application would create a transaction to call this function, and all it will get back immediately is a hash of the transaction, the ID of the transaction. Because if you think, there's quite a disconnect. So that transaction has to be created, sent off to the blockchain. It has to be mined, put into a block, and then the block has to be passed around. So it could be 15 to 20 seconds after the transaction is created before this function actually runs. So even though somebody is calling this from an external process, they wouldn't see this return value. It would be seen if you call this from an internal function, or a function that's inside the contract, but not if it's done from an external application. And we'll see how you get around those in a minute. But this gives our function a bit more usability, and allows us to set the score and then to get it afterwards as well. But the drawback that we have now, as I mentioned, is that we don't really know who is calling these functions, and it may be the case that we don't want just anybody to be able to call this function and to be able to change the score. For that reason, we use something called modifiers. So we're effectively changing the permissions around who can call this function. And again, I'll just post. I didn't post that function. Let me post that to chat. And then we want a what's called a modifier. So this is something we declare outside our functions. It belongs to the contract as a whole. And it is a means of restricting who can call a particular function. And the way to think about modifiers is to think that they wrap around a function. So what I'm going to do is to use this modifier on my set score function. And I do this by adding the name of the modifier here. So what I'm doing is I'm saying this function is now modified. It is restricted by this modifier. So the way it works is that when somebody tries to call this function, before they actually get into the function, they have to go through this modifier code. And this modifier code we're going to use to check who is allowed to call the function and to make sure it is people that we want it to be. Now we've got an error here because I haven't declared all the variables that I want. But what this modifier is doing, and I've written this in a way that really shows what the modifier is doing. There are simpler ways to write this, but I wanted to show it in more detail. What this is doing is it's comparing this message sender variable with an owner variable. And when I said it wraps around the function, you can think of the function as being put where we have this underscore. So we have this if statement, which is saying, is this message sender the same as the owner? So I'm saying there's going to be an owner of this contract. This is an identity. This is someone who has particular rights in this contract, has special rights, and has rights to change the score. And what we're doing is we're comparing that, the identity, the owner identity, with this value message.sender. And this message.sender is a value that is provided for you when your contract runs, and it is the Ethereum address of the direct caller of the function. So when someone tries to call this function, their address will go into message.sender, which will be compared here to a special address that we have, who is the owner of the contract. If those match, then we allow them to run this function, so we allow them to set the score. If it doesn't match, then we skip over the function and they don't change the score. Now it's objecting here because I have this owner variable that I haven't declared, so I'm going to add this here, and this is an address, sorry, a type address, and call it owner. So this address represents a special person, a special identity in Ethereum that we're going to set up that has special permissions for this contract. As we have a warning here that we're not returning, that we don't really need to return a value. So perhaps for simplicity, I'll remove this. Okay. So this now gives some security around our set score function, so only a particular person can do that. But then we face the problem that we have this owner address, but we have no way of setting it up. And we want to be able to do that, so it's a special person. But then we have kind of a chicken and egg situation in that we want to be able to change that variable, but obviously we want to have some permissions about how that is done. And the way to get around this, and a very standard pattern within Solidity, is to use what's called a constructor. Okay, which I haven't got something right. So we use a keyword constructor, and then what we're going to do is to use this constructor to initially set our owner. Now, the reason I say this is to initially set our owner is because the constructor is a very special function that is called only when the contract is deployed. And in fact, it's not actually included in the bytecode that is on the blockchain because it's never going to be called again, so it would be a waste of space. So this function is called in the deployment of your contract, so as the contract is being added to the blockchain, but it is never used after that. So as our contract is deployed, we are going to take the value of the person who issued that transaction and make that to be the owner. So our special identity is going to be the person who deployed the contract. It's quite a neat way to do it. I'll just copy that into the chat. So that's the way of setting up our owner initially. Okay, I've got plenty of time. So, so that takes care of setting up our owner. allowing our functions to be restricted in who can call them. But there are other things that we want to do. So we have a question. Is the modifier circular with the constructor? I'm not sure what I mean by that exactly, but the constructor and the modifiers are separate. You can have multiple modifiers. They are quite separate to the constructor. So we're not modifying the constructor in any way here. We're not making any restrictions on the constructor here. So the person who's going to be initially set as the owner will be the person who deploys the contract, which is a reasonable assumption. The person who developed the contract, who deploys it, should have special permissions. In a real world example, we'd also then have extra code so that we could change this value of owner and set it to be other people. And then we would have modifiers on the function that allowed us to do that, for example. Okay, so the thing I want to look at next is the concept of events. So let me just copy one of those. Yeah. Now, as I said, when you have a function that is making a change to the contract, this needs a transaction to do it, but we don't see the result of this. So although this is a very simple function here, if you imagine the function was more complex, we may not know, the calling application would want to know what happened in that function and may want to have a return result, but it is not something we can easily get back into an external application. And for that, we use things called events. And the way to think about events is really as if they are logging, doing a log statement from your contract. Excuse me. So I'm going to use this event to signal that someone has changed the score and what the score has been changed to. So I've created this event here. I've defined it. So we need the keyword event. It needs a name. And then it takes some parameters. We can put, you don't need to name these parameters. In fact, let me take that out for the moment. You can just put the type of, the data type in there, or you can name them if you want. And you can also, as you saw then, have them indexed. This is just for optimization when you're looking at them externally. But the event we're going to use to show that our set score function has been called and that it has run successfully and that the score has changed. And so to emit this event, to log this detail to the blockchain, we use the emit keyword followed by the name of the event and then the value. So we're going to pass in a uint256 here. So we're going to pass in the value of our score here. So this now gives us a means of when we've called our set score function, it gives us a means of signaling to the world what has happened within our function. And external applications can monitor these events and react to these events. It's important to understand that other functions within the contract cannot see this event. So you cannot use it internally within your contract. You would use other means to do that. You would call other functions directly from this function if you wanted to do that. But yeah, this is used to signal externally that something has happened. So an external application could respond to this event. Okay. So I just want to now add a couple more data types just to introduce them to you. So we've already seen a numeric data type, uint256. We've seen an address. This is an Ethereum address, an identity on the application. Other useful ones that you will need. You can have strings, so something like that. So that is what is understood by string in other languages, just a set of bytes that are interpreted as a sequence of characters. And then in terms of more complex structures, we can also have arrays and mappings. And you will use these a great deal. I'm going to just paste these in to show you what they look like. So to take the array, first of all, if it's not very clear, there's got 2 square brackets there. So what we're saying is we're setting up an array of addresses. So this is what is understood by array in all other languages. It's just a number of addresses in sequence, and we give it a name. So I'm going to call this one leaderboard, for example. So very straightforward, very similar to what you see in other languages. Something a little bit different is a mapping. This is what people may have come across as dictionaries in Python or hash maps in other languages. And it represents a relationship between 2 different data types. So we're saying we're going to have a relationship between an address and a number, a uint256. And this is a way that we can associate a score with a particular address. So within our mapping, we could have a great many different addresses of different users who are using our application. And each one of those would have a score which is given by this uint256 number. And this mapping as a whole is given a name which I've called score for user. These 2 structures are very common, and you'll use these a great deal. They're a way of using simple data types. The other one that you will come across that you need to see is a struct. Again, if you've coded in traditional languages, you will probably have come across the idea of a struct. This is just of putting simple data types together into a larger and creating a lot of type out of it. I'm getting warnings that my broadband is a little unstable, so if I cut out, please let me know if the video stops being. I'll get a hotspot ready in case it does fall over. Okay. So really, those things I shared, they are the sort of the simplest, the most important parts, perhaps, of a contract. So at the top here, have skills. We have here some variables, some data types put together into a user-defined data types. Okay, sorry about this. I'll repeat that. So we have some variables. We have some data types here that are collected into a user-defined data type. We have some collections of variables here, either as maps or as an array. We have a modifier. So from this point up, these are fairly traditional. I guess you'd have seen these in any other languages. Modifiers and events are very specific to the Ethereum blockchain. But yeah, this modifier we use for security, really, to restrict who can call our functions. We have events that allow us to log things that have happened in our function calls. And then we have a constructor. So this is a function that is run just once. And then we have a number of functions of our contract where we're doing the real nitty-gritty of what we want our contract to do. So that really is perhaps the simplest contract with most of the items that you would want to use. I can point you at, I've written other tutorials and have other videos that will go through and give you more details about this if you want to look into it further. But please have a look, try this out in Remix. If you make a mistake with the syntax, you'll get errors shown by the compiler. But once it's happy, you'll get a green tick, and then you will be able to then deploy it. Ah, good, I'm glad to see. this sounds better. Good. Once you've compiled, you can deploy your contract. So here we have my contract is compiled because I can see it here, and I get a green tick from the compiler. So I can deploy it. Now I have a choice of where I'm going to deploy it. And this is given by the box at the top here. So we have a choice of 3. The one that you should use initially, the easiest one, is the JavaScript VM. So this is a little blockchain that just runs within your browser, just runs within memory. It's very fast. It does not connect with anything else. It has its own Ether, and it gives you some accounts with Ether, but this is just fake Ether. It has no real value. But it's very useful when you're first deploying a contract and first testing your contract. The other options, Web3 provider, the bottom option, you can choose that. If you choose that, it will ask you for an external node. So this is asking you for the address of a node on the blockchain that you want to connect to. So if you wanted to connect to, say, the Ethereum mainnet or a test network, and you knew the IP address of a node, you could put that in here and then use this Web3 provider to connect to that. The other option, injected Web3, uses a plugin such as Metamask. I don't know if you can see that. I don't know if that pops up on your screen, but if you have a Metamask plugin in your browser, that will be used to then connect into the blockchain. So you will choose the blockchain that you want from Metamask. Such you may choose the main network or a test network, and then you can choose the injected Web3 option here to connect through Metamask to the through to your blockchain. So you've got a question about an error. Let me just have a look at that. Okay, it is. Okay, so older versions of Solidity required you to put a visibility modifier on the constructor. It's only in recent versions that you don't need to do that. It was a strange thing to do. It felt an odd thing because you would want your constructor to be visible because you want to be able to deploy your contract. So yeah, if you use a later version of Solidity, that should disappear, or you can just put the public keyword after the parentheses, and that should fix it. Okay. So just to go back to our deployment. So I've got my compiled contract. I've got chosen my environment. I just want to deploy it to my in-memory blockchain. I could choose an account this is going to be deployed by. All these accounts have a balance of Ether, which we need to pay for the gas for our deployment. But it's, as I say, it's fake Ether. So I'll just choose the default, the top account. You don't need to alter these values. Don't put anything here into this value field at this point. If you put something there, what that means is that as well as creating a transaction and sending that off to the blockchain, you're also sending some Ether along with your transaction, which we don't want to do in this case. So we're just going to do a deployment. So all I do is click the deploy button, and the area at the bottom here, if I can just expand that. Oops. This, let me just clear that as well. This will give you the results of what's happening when you try to do the deployment. The question, fake Ether as in Robston, no, this Ether just exists in my browser. The Robston Ether is separate again. But it is just as valueless. It's harder to get hold of Robston Ether, whereas this Ether is, this Ether you have here will be replenished every time you open up your browser. But it is just as fake, just as worthless. Okay, so I'll deploy my contract, and it deploys very quickly. You see, immediately we get a green tick and a message down here to say what has happened. If you were deploying this on a real blockchain, you would have to wait. It would be maybe 15 seconds before you got back a result to say that your contract had deployed. If you want to see more details, you can click the down arrow here and it gives you more details of what has happened with your transaction. So it tells you about the gas that was used, for example. It shows you the transaction hash, the ID of the transaction. And this part here, the logs column, or sorry, the logs row, shows you any events that happened in your transaction. So if we're running a transaction calling a function that has events, and events are emitted in that function, we would see those events being printed out here. So it's worthwhile remembering that. Okay, but that has deployed my transaction to my little browser network, and it comes up here. It shows me that it has been deployed. It shows me the address that it was deployed at, which says it's in memory. And we can use this area here to interact with my contract. Yeah, I'll copy the whole thing here. Whoops. Okay, there you go. So we can use this area here to interact with my contract. You'll see different colored buttons. The bluey-gray button is calling functions that are view functions. So these are functions that just read state. The orange buttons are functions that set state, so that change the state of our contract. So if we call getScore function, you can see it comes back with a value 0. It tells us the data type as well and comes back with a 0. And this is because this is just the default value because we haven't set it yet. If I then set the value, and I set it to be 13, we see that the contract runs and we get a tick. And so that should have run our setScore function. If we look in here, we can see the event that was emitted. So we have an event in our logs area, which includes the new score. You see here 13, amongst a lot of other detail. And then if I call my getScore function again to read from the contract, you'll see that the score variable has now been updated to 13. So you can see that that is this contract that is running, or you can see those functions that are running. So that, if you're using Remix, this workflow is what you will be doing most of the time. You'll be writing your contract, making sure it compiles, deploying it probably to your in-browser blockchain, and then interacting with it via the buttons that you have at the bottom left. Okay. So that's, I think, a good, great deal of information about Solidity, probably as much as you'd want to take in all at once. So I'll finish the Solidity part there, but please, if you have questions, do ask them.
I have a question, Laurence.
Yeah.
I was wondering, essentially, like, if one were to want to launch their own token on the Ethereum network,
Yeah.
how much work would they need to do that in terms of code, or is there code out there they can just pinch?
Yes, there is. In fact, I'll come on to that in a second. I don't know if I don't have an example here in Remix, but I can show you. It's trivially easy to create a token. It really is very easy. And in fact, yeah, I'll show you the code that you need to do that. And I think the ease of which you can do this was one of the reasons we had the ICO boom back in 2017, because it was just so simple to do. And now there are libraries available that will do all of it for you. That yeah, anybody can set up a token of their own and put that on the Ethereum blockchain and have and make it available. So yeah, it's trivially easy. Okay, so I'll go back to the slides. Okay. Actually, let me. I'll just skip forward a couple because I have exactly that slide for that question. So this is the standard interface for tokens on the Ethereum blockchain. What's called an ERC20 token. So this was a standard that was set up, which defined the functions that would be in a smart contract that define a token. And because it was an accepted standard, it meant that exchanges and wallets and other smart contracts would know how to interact with it. So it really makes it, as simple as possible to get your token adopted. And the functions that you need, very simple. So we have really the top three are the simplest ones. The first one, total supply, just says how many tokens are available in total in your contract. So maybe you will launch your token and decide that there will be 10 million tokens available initially, and whether the supply will change or not is up to you, but initially that is what you would get if you call the total supply function. Balance of is the function that you call to get a user's balance. So if a particular wallet, a particular user has a balance of these tokens, they call balance of, and that will return the amount they have. Transfer is the function that you call to transfer tokens between different addresses. So if you want to send some tokens to somebody else, you will call that one. The next three functions are really used in decentralized exchanges. Because decentralized exchanges want the ability to move tokens on your behalf, we have the transfer from function, the one at the bottom. And this allows an exchange to move some of your tokens from your account to somebody else's account. But obviously you need security around that. And so the approve function has to be called first. So you would approve a decentralized exchange to spend tokens on your behalf, and then they could then call the transfer from function to do that. And if they want to check, or you want to check how many tokens you have approved, you can call the allowance function to do that. And the two events you see there are the events that we need to indicate what's going on in our contract. So these are called, when tokens are transferred, you get the transfer event saying, who sent tokens to whom and how many were sent. And then the approval event is sent if you're showing that you've made an approval. Okay, so that's the interface. That's the standard contract. In fact, this is all written in a library. So there's a project called Open Zeppelin who have libraries, and they do all of this for you. If you want to write a contract that does it, you don't even have to implement all of these yourself. You can just inherit from this library, effectively include this library in your code, and maybe just have a constructor function in your contract which says how many tokens you want to mint, how many tokens you want in your initial supply, and that's all you need to do. So really, it's one line of code to create your own token contract. So very easy indeed. Okay, I was just going to say a couple of things about best practices. So please do use libraries such as Open Zeppelin. So these are open source libraries written by some very clever people. They have been audited. They've had a lot of eyes on them. So please use those as much as you can. It saves you having to reinvent the wheel. They've got libraries for all of the common things that you want to do. And in fact, the example I had in my contract of setting up the owner and of checking who the owner is, all of that is done by Open Zeppelin. I did that to show you the concept, but you don't need to do that. You can get Open Zeppelin to do that for you. Please, if you're doing this and there's any kind of money involved or any kind of value in your contract, or even just reputational value, please get your code audited. It's so easy to make a mistake or miss something that could cause big problems down the line. And there are so many examples of where security has gone wrong, where contracts have gone wrong. We had Someone quoted the example earlier on of $50 million being lost. That was a simple example of some statements in a contract that were in the wrong order, and meant that millions of dollars were lost. So please get some other people to look at your code, get it audited. There are the companies that do that. I mean, we do this. There are other companies that do this. There are plenty of resources if you want to do this, but it's probably best to have someone else look at your code because they won't have the same preconceptions that you do. They're more likely to spot any mistakes you've made. But yeah, please do that. And assume that the environment you're deploying to is full of malicious hackers who are going to do their best to steal your crypto in your contract or to break your contract in some way. A good thing to do is to have some kind of escape hatch in your contract. This goes against the principle of autonomy or decentralization a little bit, but it may be you could have a special user, an admin user, who has a means of pausing your contract or changing, reverting transactions to some extent, or fixing problems. It's very useful to do that, certainly initially, just in case it's something you haven't thought of. You could stop your contract, give yourself time to look at it, see what's going on, and perhaps you would get rid of this functionality after a year when you can be more sure that your contract is working properly. And something that tends to be a big problem with in blockchain applications generally is the UI. So please write a user-friendly UI, something that is intuitive and easy for people to use. It's an area that we've really failed to do over the years. The developers have really written for themselves and other people who already understand crypto and understand smart contracts. But for people who've not come across these before, please write a user-friendly UI. Don't assume your data is private. If you're talking about Ethereum, nothing that you put in a smart contract or in a transaction going to a smart contract is private. Every piece of data that goes onto the Ethereum blockchain can be seen by someone who wants to see it. So be careful about that. If that brings you on to the next point about personal data, GDPR restrictions make it problematic if you put personal data onto the blockchain. The best thing is just to avoid getting personal data anywhere near the blockchain. People have a right to be forgotten. Once you've put data onto the blockchain, you cannot effectively delete it because there'll always be that transaction on the blockchain that puts it there. So that then goes against people's rights to be forgotten. So be very careful about personal data. Don't assume that a particular user is online when your transaction is running. Maybe that for whatever reason they're not there. They may be deliberately offline. They may have problems, whatever, but they don't assume that, and neither assume that a particular order of transactions will be followed. It is up to the miner to decide which transactions are included in a block and what order those transactions go in. There's a whole topic, a very interesting area about front running that I don't have time to go into now, but you also need to be careful that people can put transactions in front of your transaction as well. So do be careful about that. And that does happen and is causing a problem in decentralized finance applications. There's a great place, once you've started writing applications, Consensus have a good site of best practices. I won't go through those because you really do need to have more information about Solidity to understand a lot of these, but have a look at that link and follow their best practices. There's a lot of good advice there. We've covered ERC20 tokens. Next week, we will look at how you interact with your contract. So what I have covered so far is very much about writing the contract and very much focused on that environment and the contract within the EVM. I haven't really said much about how you can interact with that. I've mentioned that we would interact with it, and and this is where external functions are called, but I haven't said how to do that. There are libraries that will allow you to do that in a number of languages. The most popular one, I guess, is a JavaScript library called Web3.js, but there are other ones. I'm sorry, there's a typo in the slide here. So there are other ones in Java, in Rust, and .NET, PHP, whatever you want. But we'll be talking about those in the next session. We'll be showing you how to write the application that wraps around your smart contract and interacts with your smart contract. Okay. We'll also be looking at other development tools. So a great tool is Truffle, which helps you to automate a lot of the work that you want to do. It allows you to set up unit tests, which is always a good idea. I wouldn't recommend it for when you first start because it's just command line. It doesn't give you the instant feedback that Remix does. So I think when you're initially writing your contract, it's easier to write it on Remix and then move on to Truffle later. But again, we'll talk about that next week. We have a number of resources to help you write your applications. So we have our community education site. Please go to that, have a look. We have workshops about writing smart contracts. We have videos and step-by-step tutorials about that, about writing Solidity smart contracts, and then also about writing dApps. We have tutorials about security, and general introductions to blockchain and DeFi. We also have a game we've just introduced, a capture the flag. So hopefully I emphasize that security is very important when you're writing your contracts. This game lets you test out your understanding of security. So it's a traditional security game of capture the flag. We add new levels to this every so often. So go have a look at that, have a play at that. I think it's on the Rinkeby network, so you're not going to have to pay any transaction fees to play it. It allows you to test out your knowledge of security. So please make the most of that website. I hope you find it useful. That's it. I've given you quite a lot of information. So well done. I hope I haven't overloaded you. I'm happy to answer more questions, or if you want to ask questions later, yeah, please do get in touch with me. I'm happy to answer them then. Just to mention, the next session next week, the third one, it will be my colleague Tom who is going to be running that. He's very good at explaining how to write decentralized apps. So it'll be him running that. But certainly, yeah, he will be able to also to answer any questions about Solidity. But if you have any in the meantime, I'm happy to answer them now. Or if you want to email them to me, that's also fine. Shall I stop sharing my screen, perhaps?
Awesome. Any questions? Any questions? Now's a great time to ask. As Laurence said, it'll be Tom next week, but I'm sure Tom can answer your questions as well. So
yeah.
Hi, I just had a question. I didn't attend the first session, so maybe it's specific to me, but I would just love to know the big picture of how you would deploy an app from beginning till the end, because you mentioned Solidity, and then you mentioned that's just the contract, right? Mm-hmm. Eventually, you're going to be interacting with a JavaScript library, and then you need to build a UI, and you probably need to deploy it somewhere else where it can be used. I mean, to develop a real-world application, how do you go from the thing that we did today on Remix to actually being developing an actual app that is going to be used by somebody?
Okay.
So I think there was this application which was a decentralized application, which was probably the #1 application I just saw a few weeks ago, was that it rewards you points when you exercise. Because of COVID-19, people were not exercising, so it was one of those apps which was being usable and downable. And yeah.
So so what I've covered today is just the smart contract side. So so that's the first part that you would do. So you would want to write your smart contract, and you can use Remix to do this. You can use Remix to deploy that to the Ethereum mainnet as well. Obviously, you'd want to do it to test nets first, but you can use Remix to do the whole deploy process and do that. And then, yes, you need another part, which is the interface to that application. That is something that we will be talking about in the next session, showing you how to do that. But typically, there are different things you could do for that, but maybe, and imagine with your example, it would be something you have on your phone. So somebody will have written an application, probably in something like JavaScript or maybe React Native, whatever language they've done. But they've written an application which then makes calls via the libraries I mentioned, these Web3 libraries. It makes calls from there into the blockchain and into your contract. So you have the application sitting on your phone. You would have created a wallet. You will have your keys on the phone. You will create the transaction on your phone, and that will get passed via these libraries to the blockchain, and that will then interact with your contract and do whatever it is that your application is doing.
Right. Thank you so much. This puts things into perspective much better.
Yeah. But we will be going through that in the next session, exactly how you write these applications and then how you interact with your contracts. I'll do that.
Wonderful. Thank you so much.
Pleasure.
Awesome. And before we head off, so we have a raffle winner for tonight, and that is Will in the participants list. So please come on down, Will, and claim your prize. Okay, awesome. So Will, yeah, just drop me an email at president@oxfordblockchain.co.uk with your Ether address, and we'll be sending 0.1 Ether to you fairly soon. There's going to be more winnings to be had at the next event and the event after that. So there's a bit of a theme. Before we end, any more questions for Laurence? Okay.
I think I will have a last question about formal verification and security. Are we going to cover that through this course or this series, or is that something we just will?
Yeah, I hadn't intended to, but I'll do that in the last session where we're looking at other technologies. I'll talk a little bit about that. Yeah, interestingly, that's a very interesting area. There's a lot of research going on into that, and a lot of that was prompted by the attack that happened on the DAO, and when people realised the potential damage that could happen if there is a bug in your contract, then people started to look at means of formally verifying what your contract does. But I think it is still fairly early days compared to sort of formal verification of traditional languages. But yeah, it's a very interesting area, and I'll create some slides about that for session 4. Yeah.
That sounds great. It's always good to know when a new thing is starting up before it gets popular. That's when you can contribute, right? Yeah.
No, there's plenty in this area. So yeah.
Good. Thank you.
Pleasure.
Yeah, great question. And thanks again, Laurence, for a great session. I've got a few messages from people privately saying they've really enjoyed it.
Good.
So once again, if you missed anything or if you want to catch up on the first session, the video is available on our YouTube channel. There's also a Medium post with the slides. All of this can be found via our website at oxfordblockchain.co.uk. But massive thank you again to Laurence. And I also do advise everyone to check out the educational material that xtrp.io have. So, because that's something I've played around with a few times, and it seems like it's growing, especially the sound of a game as well. That sounds quite cool.
Yeah, please play. Yeah.
But yeah, so thanks a lot, everyone. Hope to see you at the next event, which will be, I think, next week Tuesday, and then the fourth one will be Wednesday. Yeah. So looking forward to seeing you there. And any other questions, just send me an email. and we'll try and deal with them as best as we can. But yeah, thanks again, and thanks, Laurence. Thanks a lot, and hope you all have a great evening.
Thank you.
Thanks, Brandon. Bye bye.
No worries. Thanks. Great questions as well. Keep them coming.
Yeah, I really like the interactive session. It's nice to know.
Oh yeah, definitely.
This is my first time at the Oxford blockchain event, so this is wonderful.
Yeah. A few people couldn't join in the start because the Zoom link was buggy. So it was the right address, but the hyperlink underneath the link was going to a different yesterday's meeting. So it's really good that we're recording these, and then also anyone who has access to YouTube can watch them as well. But yeah, thanks. And honestly, any question's a great question. So, and Laurence loves it as well. I remember going to these a year ago and just like having my hand up the whole time because I had no clue what was going on. I didn't even know how to run the script. So.
Yeah, it's fine. It's completely fine. Nice to meet you.
Yeah,
I'll see you next week.
Awesome. Okay. See you guys next week. See everyone next week. And thanks again, Akansha. Thanks again.
My pleasure. Take care.
Bye.
Bye.